Hi, so today we are going to look at the density of the log problem. And it's basically there's a log floating in the lake, and we want to know what the density of the log is by only knowing the height of the log that's poking above the water and the radius of the log, assuming this log is a perfect cylinder. So let's get started. So we know that if this log is sitting still, that the log is displacing some amount of water, some amount of fluid. And what we know about buoyancy is that it's the weight of the fluid displaced. So our buoyant force is equal to weight of the log, right? Well, weight of the log is m is the mass of the log times our gravitational constant. And that is equal to our mass of the water displaced times our gravitational constant. Well, there's a g on both sides, so we get rid of that g constant. So now we're just left with mass. Well, mass is also equal, and this is how we're actually going to get to our densities. And so mass is equal to for the water, density of the water, which we are going to signify by the letter rho, multiplied by the cross-sectional area of what's under the water. So that's I did that by the shape of the log. So I'm going to make a little note here. I cannot spell. And then that is equal to our density of the log, which is what we're ultimately trying to find, multiplied by the entire cross-sectional area of the log, which in this case is a perfect circle. So that would just be pi r squared. So we're close, and so we need to find the area of the cross-sectional area of the area under the water of what the log is. And so we know that our area of the circle minus a little top, like moon shape, if you will, is equal to this. And this shape is equal to our circular sector minus the triangle. And we can actually identify this triangle as kind of this right here, and that is also r. So what we need to do ultimately is find the area of this. And so really the next step is to find the area of the circular sector. Well, the area of the circular sector is the angle. I'm going to redraw this. This angle, which in this case, this is theta, and this is theta, so we'll call that 2 theta, divided by the number of radians in a circle, multiplied by the entire area of a circle, which is pi r squared. Well, conveniently, a lot of this stuff cancels out. Our 2's cancel out and our pi's cancel out. So really, our area is equal to theta which is our angle, times our radius squared. Well, we don't know theta, and we want to find the density in terms of r and h. But we can do this by using a simple trig substitution, by using the arc cosine of r minus h over r, using our triangle up here with these two values. And since r is adjacent, that kind of thing, or r minus h is adjacent. So now our area, if I could spell, is equal to the arc cosine of r minus h over r times r squared. Cool, so we have our area of the full circular sector, which is right here. But now we need to subtract the area of the triangle. So, well, looking at our triangle, we have a base here and a base here. We'll just denote it as x. And so our area of the triangle is 1/2 times x times our height, which we saw up here, is r minus h. Well, we don't know what x is, and again, we wanted to try to find this in terms of r and h. Well, we can do this pretty easily by using the Pythagorean theorem. So r squared is equal to x squared plus r minus h squared. So that means that r squared minus r minus h squared is equal to x squared. And we're going to get something that eventually cancels out. And so what we want is to expand this out. And don't judge me, I still like to expand these to make sure I'm not making a silly mistake. That should match. Yep, okay. And so now r squared minus r squared plus 2rh minus h squared is equal to x squared. These cancel out conveniently. Square root both sides. Now we know x to be the square root of 2rh minus h squared. Cool, so we have our x in terms of r and h. So we're actually really close. So again, we said that our area of the triangle was 1/2 base times height, which our base is now 2rh minus h squared, and times our height, which is r minus h. But that was just for this little piece right here. We also need to do this. That's why we need to multiply this whole thing by 2. So now our area of the triangle is right here. And what we said before is that our area of the circular sector minus the area of the triangle is the area of this little top piece, which is what we were looking for. Well, we know that the area of the circular sector is right up here. So the arc cosine r minus h over r times r squared minus our area of the triangle is giving us our area of the top piece. Now we subtract the area of the top piece from the full circle to get the cross-sectional area of our piece of the log that's submerged underneath the water. So now if we do pi r squared, which is the area of a circle, minus cosine r minus h over r times r squared minus this full area of the triangle that gives us the cross-sectional area of what's under the log. Well, cross-sectional area of what's under the log divided by, multiplied by the density of the water divided by pi r squared is going to give our density, is what we're looking for. Well, we know, let's go ahead and divide pi r squared. And we also know that the density of water is 1,000 kilograms per cubic meter. So multiply this by 1,000, and this equals, and this is our full density. Density of the log. And so this is the equation that will equate our radius, our height, to our density of the log that we were given. So that is how you solve the density of the log problem. Thank you.